Hi, my name is Ignacio Lopez and I'm going to present you the effect of milling processes on the magnetic properties of iron, nickel, cobalt soft magnetic materials. Well, this work reports the effect of the formation and lattice strain obtained by low energy ball milling in soft magnetic particles as soft magnetic materials. It has been observed that the low energy of the ball milling changes the magnetic domain size, increasing magnetization, remanence, and magnetic permeability of the milled powders as ferromagnetic particles. It is due to the increase of linear defects at the increase of lattice strain. Well, the magnetization MS increased up to 70% by the accumulation of crystalline defects, although the MS decreases with the reduction of particle size due to the connection of voids between the lines of magnetization across the crystalline defects obtained by milling. The response is produced by the cold working through the ball milling. Well, as introduction, we have the soft magnetic materials are materials made by ferromagnetic powders particles or some alloys made by ferromagnetic elements. Well, this kind of materials can be used as an efficient flux multiplier used in some devices including motors, generators, and transformers. Also used in the generation, distribution, and conversion of electrical energy. Well, the soft magnetic materials possess high magnetic permeability, high electrical resistivity, good relatively permeability, and magnetic saturation. Well, low coercitivity and very low eddy current loss properties. Well, these ferromagnetic powders obtained by large amount of process used to obtain soft magnetic materials can be used to manufacture by some routes. One of the most important recently are the additive manufacture. Well, these materials are also used in mixed with polymeric matrix to manufacture soft magnetic composites that have three-dimensional isotropic ferromagnetic behavior. It has also been observed how the mechanical milling can change the magnetic performance in ferromagnetic particles, modifying the saturation, magnetization, permeability, and coercitivity produced by the reduction of particle size which reduce the magnetic domain size. Well, the changes of magnetization are directly related to the particle size, reduced by long times of milling, as seen in works where they have obtained ferromagnetic nanoparticles and amorphous powders. It has been reported that system iron, nickel, cobalt magnetization increases during the first step of milling, but the phenomenon is not clearly understood yet. Well, in another study carried out in ferromagnetic hard alloys, it has been observed that the increment of such properties is related to the accumulation of defects that change the magnetic domain size. Well, this later can be attributed to the lattice strain during the milling process. In this work, the microstructural and mechanical characterization of soft magnetic iron, nickel, cobalt material were investigated. In the order to carry out our study, powders of these elements were firstly mechanical milled and at different conditions to obtain different shapes and particle size, which for instance induced deformation and lattice strain, conveying to the enhance of the magnetic properties. In this way, can be measured any change in the magnetic behavior due to the milling process to obtain soft magnetic materials with high magnetization compared with the started systems without deformation, also improving the remanence, magnetic permeability, and electrical resistivity just by increasing the lattice strain and defect density. Well, some of the materials and methods are where we used commercial powders of iron, nickel, and cobalt with high purity and the particle size around 130, 10, and 12 micrometers respectively. This composition has shown the best magnetic performance both in magnetization and magnetic permeability, carried out in previous works. The morphology and particle size were analyzed by scanning an electron microscope in order to analyze by SEM the ferromagnetic powders were placed on a removable substrate to prevent the movement of the particles, for their magnetic behavior. In the case of milling process, in order to analyze the effect of magnetic properties, one mixture system of iron, nickel, and cobalt having 45, 45, and 10% respectively was obtained at different low energy ball millings from 0 to 10 hours with a jump of 2 hours respectively. The conditions of mill were ball to powder weight ratio of 10:1 and the vial radius speed was 100 revolution per minute, due to the need to promote the homogeneous mixture using low energy ball milling. Unrelated to the increase in magnetization can be obtained between the time conditions. The powders were introduced in a cylindrical vial with stainless balls to minimize the oxidation of particles. In case of characterization, the changes in crystallinity were investigated by the details of relatively broadening 110 breaks of the nickel and iron nickel cobalt after milling using the fuel width at half maximum analysis by X-ray diffraction method. The characterization of magnetization, remanence, permeability, and coercitivity values were obtained by a variable field translation balance with 20 milligrams of sample and magnetic field from 0 to 10 milliteslas at a frequency of 3.9 Hz. The magnetic susceptibility study was carried out using a frequency-dependent magnetic susceptibility analyzer. At alternating current, the frequency range was from 10 Hz to 25 kHz at 100 milligauss. In case of the results that can be seen in the figure 2 of the poster, we see the measurements of the full width at half maximum over the intensity. These measurements were obtained to qualitatively identify critical points of the deformation and lattice strength and of the particles, as can be seen from 0 to 6 hours of mechanical milling. The particles accumulated deformation by mechanical milling until the particles tend to release energy due to the saturation of this deformation. From 6 hours of milling, the particles stopped accumulating deformation and being to reduce the particle size without more deformation. As can be seen in figure 3 of the poster, show the morphologies and distribution of the metals after mechanical milling according to the chemical mapping obtained by scanning electron microscopy. It is observed that from 2 hours of milling, the nickel and cobalt particles began to flatten and coat the iron particles. The iron particles are deformed in the same way as those are of nickel and cobalt. In case of 8 and 10 hours of milling does not show a considerable change in particle size. Both nickel and cobalt particles are accumulating surround over the iron particles. In this case, the iron particles accumulated deformation until 6 hours of milling. At this step, they began to fracture and reducing the particle size as milling time was increasing. Although this reduction was not significant, since it is known to reduce the size in a major manner by mechanical milling, it is necessary times longer than 20 hours at 300 revolution per minute. has not been reported a change of the particle size morphology for any particular system in most cases. These effects tends to be related to mechanical milling modeling. Well, the flake-like morphology obtained in the present study, it is due by the centrifugal forces and the Coriolis effect between the wall of the vial and the milling valves carried out in one direction. This is for the 10 hours and 8 hours of milling. Well, on the other hand, in figure 4, shows the relation of, in case of A, magnetization and coercitivity, in case of B, remanence and lattice strain, in case of C, permeability and susceptibility, and in case of D, magnetic susceptibility and frequency. Well, it is observed that magnetization, permeability, and remanence have the same tendency to increase with the increasing of milling time until 4 hours. Then these properties decrease as the time increased. It is due for the reduction of particle size. Well, this can be related in this case to the particles fracturing, since this started cracking due to the accumulation of tension. Then this tension tends to decrease as the particle size was smaller. Thus, these properties were directly associated to the deformation analysis in lattice strain, which represents an enhance with the increase in the density of dislocations and defects in the particles due to the mechanical milling. It is well known that the mechanical flux lines tend to circumvent macrometric defects, but in this case the defects had a size of a Burger vector or a punctual defect. Then these defects operate as an interconnection, thus causing a larger total magnetic domain size, and therefore these properties increased. Well, in the case of coercitivity, this increased linearly with the increment in milling time, since although the particles were very deformed and did not keep accumulating tension at the point where when the particles started fracturing, more obstacles were generated to prevent the change of the direction of magnetic domains that characterizes the coercivity. Well, this phenomenon has not been studied in detail, but it has been observed in systems in which it has intent to reach particles in a nanoscale size by high energy ball milling for long periods. It was also observed that the short times of ball milling occurred an increasing in magnetization, which has been generally attributed to the formation of defects by milling, but it has not been explained in detail how these defects interact with the magnetic domains. This type of rise in magnetization is also observed in hard magnetic alloys, in which the main objective it was the enhance of magnetization and coercitivity, but only an increment up to 15% was achieved. Thus, through the lattice strain analysis, it can be identified that such increment was completely related to the cold work obtained by mechanical milling and was due to the connections between the magnetic domains, increasing the magnitude of the total magnetization. As conclusion, well, the strain generated on the metallic and magnetic powders by the milling process influenced the magnetic properties on both the mixed systems without compaction and the soft magnetic composites. The magnetic saturation increased with the increment of lattice strain until the particles decrease due to the saturation of tension in the particles. Well, 78% in magnetization for 4 hours of milling was reached. In the case of milling system, the coercitivity increased linearly as the lattice strain increased increase too, due to the defects prevents the change of direction of these magnetic domains. The analysis of the accumulation of lattice strain is effective to identify the accumulation of this tension in the particles and directly attribute their magnetic properties to the powders. Well, we would like to thank the Universidad Michoacana San Nicolás de Hidalgo and the Instituto de Investigación en Metalurgia y Materiales and the Universidad Nacional Autónoma de México with their Instituto de Geofísica and the CONACYT for the support of this work. I would like to thank you for this time and see you later.